We're looking at the two ways of defining a sequence here, and here we've got 5 sequences you probably recognise. Before we do that, I'm going to do a few little definitions, a way we define, a bit of notation, how we write things when we're talking about sequences. First of all, we can see the first term here is 2, the first term there is 1, the first term there is 1, and so on. But we want to have some mathematical way of writing the first term without it being a load of words. That's what maths is about, it's a language. So we tend to use this notation, this suffix notation, U1. Now it's very important that 1, you see, is actually written below the U. It's not a number in the sense you're timesing by 1. That just means the first term. It is a suffix. Okay, and U2, U3, U4, U5, U6, and then of course what we can do, and you will have all seen the idea of an nth term. Okay, so this we can talk about first term, second term, third term, fourth term, fifth term, sixth term, and nth term. Now, some of these sequences are going to be easy to give an nth term formula for, and that's one of the ways of defining a sequence. Just saying what un is here in terms of n. Okay, so that's one of the ways. Now, in this case, we would say it's fairly easy to see what the unth term is here, isn't it? We can say it's just double whatever the term number is. So we've got here, we just, so what is the unth term? 2n, exactly. 2 times whatever the value of n is. So you can see how powerful this is, although you might think it's reasonably simple. It means that we've got a way of writing the second term without just writing out the word second term. And then we can see this number here represents the position it is in the term. So then that's 4, for example, for the second term. So our formula is just simply un equals 2n. That's my nth term formula. You might have heard the expression, I don't know if it's used so much these days, position to term rule. This is sometimes called a position to term rule, because what we're doing is we're defining the nth term in terms of its position. Okay. Right. Okay. So this sequence here, a little bit, it can be expressed in terms of an nth term, but not the second one, that is. It can be expressed in terms of the nth term, but you need to be careful. We've done work in logs just recently, and powers and exponentials, but it does need care. Yeah, how are we going to do that? So you recognise that it's kind of 2 to the power of n. Yeah, but it's not exactly that, because if you put 1 in, you get 2, and if you put 2 in, you'd get 4, so you kind of 1 out. So how do you make it going to go 1 backwards there? 2 to the n minus 1. Sounds like a good plan. So we got un equals 2 to the n minus 1. You might have been tempted to minus 1. You might have been tempted to write this, because you think, oh yeah, it's just divided by. Of course, it's the same thing. But this bit here is slightly simplified. Your rule of indices, because you might have been tempted to say, oh yeah, when you worked out 2n, divide each of those numbers by 2. And you get our term in a sequence. Okay? Right, okay, right. Now this one here is square numbers, so hopefully we can easily see what the nth term is there. Straightforward. N squared. So un equals n squared. Okay. So, and then this one, anyone think of an nth term?
UN equals 105 take away 5n.
105 take away, well done, 105 take away 5n. Okay, does anyone want to have a stab at the nth term of this one? What do you do?
I can see it gets a little bit messy near the beginning, but I think most of it looks like UN equals UN minus 1 plus UN minus 2.
Yeah, it's what you've said is correct, but it's not this. It's not. You're actually referring to the sequence, the number before, not its position. So you've given what's called a recursive rule, which is what we're going to talk about. It is possible. It is possible to give an nth term rule for the Fibonacci, but it is incredibly complicated. You can look it up on Wikipedia if you like. It's the kind of thing that they like to test in step papers, Cambridge exam papers, and things like that. It's quite a complicated expression involving square roots of 5, believe it or not, something like that. But it's actually not terribly easy to come up with an nth term rule in this way, where we describe the term in terms of its position. Okay, so that's the one way of expressing a sequence in terms of an nth term rule. And as we can see in number 5, the Fibonacci numbers, the nth term rule is not terribly easy. Okay, that's not an nth term rule. So we're going on to the second way of defining a sequence. That's called a recursive rule. Recursive relation, recursive rule, sometimes called iterative rule. There are other words for it. Now in this case, what we're doing is we're defining the sequence from the term before. Okay? So in this case, what we would have to do for number 1 is say that the first term, tell us what the first term is. If we know the first term, we can get all the other terms by adding 2 to the term before. Well, so in other words, U2 is equal to 2 plus U1. U3 is equal to 2 plus U2, and so on. But we want to write that in a general way. We don't want to just... So, any ideas how we could write that in some kind of general way? So that's basically saying the next term is 2 from the one before. Okay, you could do n minus 1. Sometimes some people do it that way. I'm going to do n plus 1 to say the next one, but it's not wrong. It wouldn't be wrong to put n minus 1 on the other side, so long as one is more than the other. Un plus 1 equals... How do we get un plus 1 from the term before? Well, we'd express that as un. Remember, it's important, that little suffix, so important that little suffix stays below. Do not get careless and write it like that, because then what that looks like is u times the number n. Whereas this actually refers to some point in this sequence here. So it's very important that goes below. I haven't finished it yet, though. How do we get the next term from the one before? Plus 2. There we go. So we need the first term. Now this one here is u1 equals to 1. Okay, so we've got u1 equals to 1. And so how would we get un plus 1 equals to from the term before. How do you get it? To UN is times by 2. Okay. Now, as we've said before, this number 3 is not going to be easy to express recursively. If possible. Certainly, it's impossible with just a UN. It's going to have an n in it as well, which then begs the question, how useful would a recursive relation for number 3 be? Because it's not because the number is adding a different number each time. Yes, it is add 3 here, and yes, it is add 5 here, and yes, it is add 7. I'm going to go straight to number 4. Yeah, because it's not terribly useful for in this intro stage to talk about a recursive rule for number 3. Okay, it's possible, but not particularly helpful. Okay, so then number 4, we've got again U1 equals to 100. In some ways, it's easier for this one now to come up with a recursive rule, wasn't it, in a way, than it was to come up with the nth term rule. Not that the nth term rule was terribly hard, but it is easier. U1 is equal to 100, and then UN plus 1 equals to UN minus 5. Right. Now, the Fibonacci numbers. Slightly more complicated, but it certainly is easier to express recursively than, as I said, using a general term. We need to define the first 2 numbers here. Okay, we need because you're adding 2 numbers in a sequence together, we need to give the first 2. So that gives me U1 equals 1. U2 equals 1, and the kind of rule connecting them all, I'm going to need a UN plus 2 now. Equals, yes?
U1 plus, the UN plus 1.
Yeah.
Plus UN.
Plus UN. And that's it. Okay? So that is the recursive rule. In this case, we needed both terms. Make sure you set, it looks a little bit like that's one big long line there. Make sure that it's clear that you've separated them out. Okay, I'll put a comma in between. I've run out of space here, but make sure. And that's the recursive rule. As I say, so we're looking back, we saw with the nth term rule, it wasn't terribly easy to give, to express in an nth term rule number 5, but all the others were reasonably possible. In this case, we saw that it was they were all reasonably possible apart from number 3, where it would be troublesome. So it's useful to have both ways. Okay, both ways of defining a sequence. Okay.
If you've got to define a sequence,